start recording so that I don't forget
I
that.
just did, Rudy. Go
Okay.
ahead.
All right. Well, good afternoon, everybody. My name is Rudy Shankar. I am the director of the Energy Systems Engineering program here at Lehigh University. And this is the third in the seminar series that we are offering this fall. And this is on a very topical subject, nuclear power. Specifically, nuclear power happens to be one of the dominant green resources we have. And better still, we have a very good operating history in the United States, over 6 to 7 decades. And one of the areas that we need to continue working on is the area that Clint will be talking about. I'll introduce Clint in a minute. And it is about how we could take advantage of new technologies for advanced remote monitoring and diagnostic services. So the lower we make the operations and maintenance costs, O&M as it's called, the more competitive nuclear plants would be. So I've had the good fortune of working with Clint over several decades now, especially in this area. He was the pioneer in a subject that he's going to talk about today. So Clint presently serves as the Director of Fleet Modernization for the Utility Service Alliance, acronym is USA. And in this capacity, he's a PI for implementing the Advanced Remote Monitoring and Diagnostic Services, a DOE-sponsored initiative to research, design, and develop technology-based systems across nuclear energy facilities to improve efficiencies while lowering operating expenses. Clint has 37 years of electric utility experience, including expertise gained through a variety of positions at the Comanche Peak nuclear power plant, where he was a licensed senior reactor operator, a pioneer of the industrial internet. Clint led the deployment of the world's largest wireless industrial infrastructure, supporting voice communications, mobile computing, and equipment condition monitoring at Comanche Peak. Clint was the original architect of Vistra's Power Optimization Center, or POC. Today, the POC is recognized as the gold standard for delivering advanced monitoring and diagnostic services to nuclear, fossil, and renewable generating facilities across the nation. As an entrepreneur, he successfully commercialized the model in both domestic and international markets. In collaboration with EPRI, Clint conducted basic research and was involved in the development of numerous industry guidelines for deploying advanced technologies in power stations. In the academic sector, Clint previously served on engineering advisory boards of the University of Texas at Arlington and Lehigh University. Carter was a founder and board member of Azima DLI, an internet-based advanced analytic predictive technology service provider. He holds a BS in nuclear engineering from Kansas State University, an MS in engineering from the University of North Texas, and an MBA from Texas Christian University. Well, welcome, Clint. And before you start, I just want to give you some ground rules. This talk is for 90 minutes, nominally 60 minutes for the presentation, and then Q&A for the remaining time that we have. Clint, the floor is yours.
All right. Thank you, Dr. Shankar, and good afternoon, everyone. I apologize for some technical difficulties we're having with Zoom today. So I know you can't see me, but hopefully everyone can hear me just fine, and you can see the presentation. So what I'd like to offer today is an overview of a project we call the Advanced Remote Monitoring and Diagnostics Services Project, or ARM. And the ARM project is an initiative being sponsored through a grant from the U.S. Department of Energy to help preserve the economic viability of our nation's legacy nuclear power plants. So I'm going to give you some background around the project, the external environment that drove us to this initiative, an overview of the objectives and the deliverables from the project to help preserve nuclear, and also talk about some of the technologies we're using, some of our operating experience, progress thus far, and what this whole and the promise that this kind of technology holds for nuclear as well as other energy sources as we move through industry transformation, let's say industry disruption and transformation. And so with that, we'll jump into it. So Utility Service Alliance, I am with USA. We are a not-for-profit cooperative that provides services to a number of nuclear utilities across our nation. Our utilities are typically the smaller nuclear utilities, our member utilities that have one or two reactor sites. And so we come together under the USA Alliance for the purposes of economies of scale. So we can speak at an industry level with a larger uniform voice, and then as we can go out with a larger footprint to negotiate service and equipment, materials contracts at lower price points. And so in the US, we have 8 utilities. You can see there 9 stations, 14 reactors, 15 gigawatts of generation capacity over the United States. Also, it's important to know that we also have just acquired an international member earlier this year, Korea Hydropower Nuclear, KHMP, which has now taken total generation capacity to over 35 gigawatts that are a part of that receive services through the Utility Service Alliance. And so, where did all of this start? A little bit of history around the nuclear power industry. Some of this may be familiar to some of you, but to some of you, this may be new. The nuclear power industry actually had its birth in the early 1950s, and it was President Dwight Eisenhower in the height of the Cold War with our adversary those days, the former USSR. And on the heels of the end of the Second World War that came to a close with atomic technology, President Eisenhower stood in front of the United Nations General Assembly and announced his intention to share, for the benefit of all mankind, the nuclear science that has been created by the United States. And he called this program the Atoms for Peace program. And the purpose of the Atoms for Peace program was to apply nuclear technology for the benefit of all mankind. And so, since the early 1950s, just in the United States, this is what it's looked like since President Eisenhower launched this initiative. You can see the timeline here for generation and capacity in terms of megawatts as we've grown since the 1950s through really through 2023. At our peak in the United States in 2012, on the upper right-hand corner, we had 104 operating nuclear reactors across the nation. And at that point, we started we were being forced to shut down some of our nuclear plants that couldn't economically compete. You can see here on the left, highlighted in yellow, in 2020, we were represented 55 plants, 93 reactors across 28 states. And today, that number is continuing to go down. We've lost one power station. We're down to 92 reactors. And we were generating just over 20% of our nation's electricity. And right now we're just under 20%, around 19% of total generation capacity in the United States. That, however, at 19% represents over half of the installed generation in our nation that is truly clean, carbon-free, no emissions from nuclear power. And you can see the mix there, 20% nuclear. Majority today is provided by natural gas, with coal rapidly on the decline as renewables continue to grow. And one of the benefits of nuclear that allows it to stand out from all of the renewables that are coming online is nuclear works 24/7 at capacity factors above 90%. And so when the sun doesn't shine and the wind doesn't blow, nuclear is still full on at the highest level of reliability and the highest level of industrial safety of any industry on the planet. So today's situation, I've hinted at this a little bit. Nuclear power has grown. It is now critical for maintaining our nation's energy security, stability of the electric grid as we adopt more and more intermittent renewables. And we migrate away from fossil fuel technologies. Nuclear, I think John Kerry said this last week at Atomic Industrial Forum in New York City, and he may have mentioned this at the UN as well, that the only way that we can reach our zero carbon goals, zero emissions goals without nuclear, we just can't get there. And so it is critical for maintaining our nation's, helping our nation achieve our environmental goals. Our economic competitiveness, however, is diminishing because of disruptive technologies, increasing costs and lowering market prices. Quite a disruption in the industry, and we'll talk about what's driving that here momentarily. And so, what this has resulted in, this loss of competitiveness, is we've shut down a number of nuclear power stations across the nation in recent years, all with many years left in their operating license, still performing at high levels of safety and reliability, but just can't economically compete. And so those plants have shut down, and a good portion of the existing fleet is threatened as well unless our economics change. And so if we're going to sustain nuclear, we must reduce our operating expenses, technologically innovate, and transform our business processes. And we need to accelerate this process if we are going to preserve legacy nuclear. And so what's driving all of this? Well, foundationally, it's technological disruption. And it is a disruption. It's referred to as a revolution in terms of technologies, from fracking technologies to digitization technologies and automation and renewable technologies. The energy industry is going through substantial transformation and evolution. And so Klaus Schwab of the World Economic Forum, he talks about this. And he talks about this technological revolution that will fundamentally alter the way we live, work, and relate to one another. And the scope and complexity will be like nothing we've ever experienced before. And this is referred to as the Fourth Industrial Revolution. And it is a marriage of industry with advanced technologies, artificial intelligence, and so forth. This Fourth Industrial Revolution. And there's a link below where you can get to some additional background information from the World Economic Forum. And so anyway, given that we're in the Fourth Industrial Revolution, there must have been three before this, and just to kind of put this in a little context, this is really what we're talking about here. The first industrial revolution was in the 1800s when we mechanized manufacturing by harnessing the power of water and steam to run production activities. Next, we scaled up through the application in the second industrial revolution of electricity, and we, in a division of labor, we trained specialists to focus on different pieces and parts to optimize production capabilities and to facilitate mass production at scale. The third industrial revolution in the 70s brought about automation and computers and information technologies and so forth that continues to evolve ultimately to what we are now calling the fourth industrial revolution. And this represents a marriage of physical systems and cyber systems to further automate and enhance. So a lot of we hear a lot about machine learning and artificial intelligence. That's what the fourth industrial revolution is all about. And creating autonomous control systems, driverless vehicles and ocean-going carriers and that sort of thing. And so, and this is moving faster and faster. The rate at which technology is evolving today is truly exponential. So well beyond Moore's law. I think we've blasted through Moore's law and now are moving at an exponential pace. So it'd be amazing to look back 5 years, 10 years from now to see how far we've come just from today. And so, given the challenges today, what the USA Alliance, in collaboration with the United States Department of Energy and Idaho National Labs, we launched the Advanced Remote Monitoring and Diagnostic Services Project. This is a $14 million project funded through research grant. Our vision is to preserve the economic competitiveness, the viability of our nation's nuclear energy supply by transforming our core business processes through advanced technologies. You can see our member nuclear power plants and their utilities that are part of this initiative. And so we have three objectives under the current project. We're 3 years into a 4-year initiative here as part of phase 1 of the project, which is the currently funded project. And phase 1 includes 3 objectives: creation of a shared services technology platform. And this is a technology platform so that we can modernize legacy business processes. A challenge that we have in the nuclear industry, we stood up most of our generating sites in the 70s and early 80s. And when digital technologies had not yet reached production levels, so analog technologies and things done in a very manual fashion. The regulations and the overhead placed on the industry very costly and expensive. And so the idea here is to create a shared services platform that will allow us to technologically evolve. And I'll talk more about that. Second is to select nuclear business processes for digital transformation and modernization. And lastly is to demonstrate the value that 24/7 monitoring and diagnostic services can provide to the fleet of nuclear operating plants. And I'll talk about each of these. First, the shared services platform. We call it NewSuite. So the idea behind NewSuite is there are 3 pillars here that we're building NewSuite upon. First is on the upper left-hand corner is business process redesign. Again, the work processes in our nuclear plant are very manual. They've been in place for decades. And so the business process redesign, if we took and just digitized the way we do things now, we would sub-optimize. So we need to redesign these business processes and these workflow streams to consider digital technologies and the capabilities that are available today. So business process redesign in a standardized format. And then the application of analytics, both legacy first principles, basic physics, analytical capabilities, multivariate, and now artificial intelligence. And then online sensor monitoring. This is legacy installed sensors that come through the plant monitoring systems and nuclear plant computers. Also expanded sensors throughout the power plant using wireless technologies, and ultimately mobile sensing technologies, which would represent drones and robotics. And so in this new suite platform environment, we bring together these three pillars for each business process we transform. And we do this within what we call a transformation module. And this represents a standardized and integrated business solution that can be shared across participating utilities. And I'll talk a little bit more about those transformation modules as part of our second objective, the transformation of business processes to drive costs down. So these are the business processes that we've selected as part of the project, part of phase one, to modernize. So you can see starting at 12 o'clock, shiftly surveillances. So these are things that the operators do every 12 hours in a very manual fashion. And I'm not going to go through all these in detail, but automation of shiftly surveillance, automation of online thermal power plant efficiency monitoring, automation of on large scale, large equipment monitoring. We're starting with main transformers, automation of fire watches, operator inspections, monitoring of radiological environments and radiation work practices from a central location, and advanced analytics around anomaly detection. So just to give you a sense of one or two of these, at 12 o'clock, again, shiftly surveillances. Every 12 hours, we send operators at my plant, my power plant in Texas, which I'll be at this afternoon, by the way, Comanche Peak. We go into over 100 rooms and compartments every 12 hours to manually read a temperature on an analog gauge bolted to the wall. Quite time consuming. And we are installing wireless temperature transmitters as part of this project. So now, instead of spending all of these man hours every single day, we will click on the application from the control room. Those sensors will light up, send their data, evaluate it against the acceptance criteria, and print out our surveillance report with zero human effort. So that's one example. I'll give you one more at 6 o'clock. Fire watch. Anytime the fire protection system is impaired, let's say a smoke detector, for example, fails somewhere in the plant, we currently implement a manual fire watch. So that means that every hour, a human has to walk into that room where the fire detection system is impaired and check off on a clipboard, oh, no fire, and they have to be back in there within 60 minutes and do it again. And that's 24 by 365. So the idea here is to build a portable fire watch cart capability that would be rolled into that room, that would wirelessly monitor with cameras, imaging, and fire intelligent machine learning software, for example, to identify the emergence of fire, smoke detectors, thermal imaging, that sort of thing on a cart, to eliminate the human requirement to walk in and verify no fire. So again, automation of very costly processes is what this is all about. So all these modules you see are nearing completion, and we are preparing to conduct 6-month plant demonstrations in the host nuclear plants beginning in November. And that's phase one. Phase two is a second research grant application, which we have put together an application under consideration now by various Department of Energy entities, which allow us to scale this, to build out more of our processes in this environment, as well as scaling this up to production grade so that we can share it with additional utilities across the nation. And the ones highlighted in green just represent the ones that also have built-in embedded machine learning and artificial intelligence capabilities. And I'll talk more about machine learning and AI and the pieces and parts of that here momentarily. So that's business process transformation. The last objective, demonstrate 24/7 monitoring and diagnostic services. So this is the Power Optimization Center at my home company, Vistra Luminant, based in Irving, Texas, near Dallas, Texas. This center has been in operation for over 18 years. It represents a 24/7 operation monitoring not only nuclear, but coal, natural gas, renewables, also controls solar facilities across the nation from this. And the goal of this project is to demonstrate the value contribution that can be made to nuclear. So in addition to Luminant's one nuclear plant, Comanche Peak, as a part of this DOE-funded project, we're now monitoring the Columbia nuclear power plant in Washington State and the Susquehanna nuclear plant in Pennsylvania. And what's interesting about this is these three plants are from three separate utilities and are competitors. But we have managed to come together, integrate our networks, share real-time operating plant information with the goal of improving performance and reliability for all. So it's a first of its kind in the industry. We're very proud of that. And just one comment on the monitoring center. The POC represents a very essential man-machine interface. As we adopt more and more machine learning, artificial intelligence capabilities, you need human contribution to help those models continue to learn and grow. And so this type of operation is essential if artificial intelligence is going to scale across the industry. So I'll talk for just a couple of minutes about the Power Optimization Center and some of our success stories over the 18 years. There are 2 or 3 here that they're just fun to talk about. So this first one is at a coal plant. This was way back on day one in 2005 when we started it up. This coal plant was running at full power. And we turned on the POC for the first time, and we were receiving thousands and thousands of false alarms. We were scared. We're all going to get fired. We built this thing for all these millions of dollars. And, oh, what have we created? It's a monster. And then we come across this one alarm, and you see the data here on the right. We're like, that looks real. Like, what should we do? Well, let's call the control room at the power plant. So we called them. This is the Power Optimization Center in Dallas. The operators had never heard of us. You're who, you're where. We think you have a problem with one of your large air fans. And they had no alarms in the control room. But after explaining who we were, and we were in corporate offices, they said, okay, you sound like good guys, we'll go look. And what they found was one of their big air fans that provides forced air input into their boiler. They found a bearing, a massive oil leak on main drive bearing, and the draft of the fan had drawn the oil out of the bearing, and it was in catastrophic failure mode. So they were able to take that machine offline without tripping the unit and repair and get it back. So we literally saved a power plant trip and a catastrophic failure on day one. A few years later, this is one of our large natural gas plants in Texas. They started up during an ERCOT hot weather event. Grid conditions were tight. We started up this peaking unit, and we started getting alarms on their main power transformer. Hundreds of megawatts going out on the grid. And we were saying, we've got high temperatures. We advised the plant, so if that is so wrong, your monitoring system is flawed. If that was going on, we would have alarms all over the control room. But we'll go look at it for you since you called us. And when you see all these fans on the side of the transformer here on the left, so they went out there, and what they saw was all of the cooling for this transformer was off. Their lube oil pump or the oil pumps and these fans that keep the electrical windings cool as hundreds of megawatts are flowing through this thing onto the grid. All that cooling was off. this transformer was in an ultimate failure mode, and it would have, when it failed, it would have been a massive event, and that plant would have been shut down permanently, and a huge fire would have resulted. It would have caused probably a lot of damage, definitely a lot of damage. So we avoided a catastrophic failure. When they found that, they were able to go and they found a breaker, power supply breaker that had been left open from some maintenance on the end. They closed the breaker. Pumps and fans came on. You can see on the trend on the right, temperatures trended back down. Literally saved that transformer in that plant. And that plant is still running today. Here's a nuclear one. This is from a few years ago. One of the units at Comanche Peak is running at 100% power, and they have a major pump that trips offline unexpectedly. The plant by design runs back to 70% power and stabilizes. And in the monitoring center in Dallas, we started getting alarms, high temperature alarms on the pump that just tripped. So we called the control room and advised, and they said, we don't care about that pump. It tripped offline. The plant is in an upset. We're trying to stabilize things. But the POC convinced them to look, and they said, you're right. Why are the temperatures on this pump screaming up when it's offline? That shouldn't happen. They sent an operator out, and they found, as a result of the trip, a check valve that had stuck open, which was reverse flowing, making the pump spin backwards, and it isn't lubricated when it's reverse spinning. So they were able to isolate it and save catastrophic failure. So this is an example of how remote monitoring technologies, miles and miles away, can make a contribution, even at a nuclear power plant, during reactor transient conditions. Second set of eyes there to assist with success. Okay, I'm going to shift gears now. Just take a time check. Looks like I've got maybe about 20 minutes or so. So please help keep me honest.
Yeah, you're in good shape.
Okay, sounds good. So some highlights and progress on the project. So first, I want to talk about, and I think this will, as engineers, you'll find this interesting. I'm sure those of you involved in research are familiar with technology readiness levels. And so, from very, levels 1 through 9, from principles observed to ultimately proven technologies ready for prime time. And so you can see here, left to right, the different technologies that our solutions are integrating as part of the Advanced Remote Monitoring project. And you can see the technology readiness levels for each of those. So field sensing technologies, telecom, data management, man-machine interface, artificial intelligence. So you can see that's the lay of the land for us right now with the technologies that we're using. Some of you may have experienced this in your own careers, but oftentimes very promising technology-based initiatives fail, even though the technology is very valid and offers a lot of promise for innovation. Why do these technologies fail? Well, as engineers, we typically focus on the technology, but there's a much broader framework for successful transformation, technology-based transformation initiatives. And so I would encourage all of you, as you work as a part of your careers, to also consider some other areas that we need to focus on to have a complete and successful framework for transformation. And so those are on the bottom left, regulatory and market. So the idea here is, if you're going to go apply all these new technologies in nuclear power, for example, you've got all this regulatory overhead and those that manage it. You need to access those regulatory processes to get these new technologies accepted. And you're going to have to wade through the politics and the policies, prove that it's safe and reliable, and ultimately generate acceptance of that solution from your regulators, or your bureaucrats or your decision, whoever those people are that make these kind of decisions, you need to also invest time to bring them along as well from a readiness perspective. Second, you need to have market access on the right. That means that in order to sustain what you've created and built out, there has to be a market for it. There has to be commercial suppliers to maintain what you created and to further expand it. And so you've got to have access to the market. You've got to have access to capital. You've got to have the ability to manufacture. It's got to be profitable. It's got to be valuable for all stakeholders. So strongly encourage you all to think about these three readiness level categories as you have an opportunity to innovate with modern technologies as part of your initiatives. So again, you've got to have these readiness levels mature across all three of these sectors. So I'll talk a little bit about some of the things that are aligned with this. So we have created the new suite architecture. The platform is ready. We're installing sensors and edge devices, technologies, wireless infrastructure at the participating plants. We've received the codified machine learning algorithms from our research partners at Idaho National Labs. We've launched collaboration with the Nuclear Regulatory Commission, and I'll talk a little bit more about that momentarily. And we've submitted a second grant application to continue to scale this to production levels, get more commercial interest, and be able to scale this across more of the U.S. nuclear industry. So again, bringing along regulators, other stakeholders. This is at Comanche Peak from a few months ago, and the folks in the room is an entire shift complement of nuclear operators, from the shift manager, their licensed reactor operators, through their field operators, bringing them in, sharing new suite and the modules we're building. They represent the end users. Your end users never take a new technology, offering it up as a solution to stakeholders and asking them to go find a problem to put it on. You've got to bring them into the process, gather their input, get their support, get them integrated, make them feel like they're part of the solution. That was what this was all about, was to get the operators' input, as they're going to be using new suite in the future. And that's their livelihood, and they have responsibilities to safely execute operations in a nuclear power plant. So bring along your stakeholders, engage them very early in your processes. This is in Georgetown, Maryland. Germantown, Maryland, at the original, born out of the Atoms for Peace initiative in the 50s. This is the original headquarters of the Atomic Energy Commission, now Department of Energy. And we met with over 35 representatives from across the industry to overview the Advanced Monitoring Project, all the benefits, to bring along our regulator, the Nuclear Regulatory Commission. And we had 15 representatives from the Nuclear Regulatory Commission, including 4 branch chiefs that participated as part of this earlier this year. And we're continuing bringing along our regulators. We have a 3-hour call tomorrow with the Nuclear Regulatory Commission to provide them an update on the project and an overview of how our Monitoring and Diagnostics Center is helping those 3 nuclear stations and the technologies that we're using to make them successful. So bringing along our regulators so they understand and develop comfort around these technologies that we're going to be applying in our nuclear facilities. Also engaging other industry stakeholders. The Nuclear Energy Institute, based in Washington, D.C., is the nuclear power industry's lobbying entity inside the Beltway in Washington, D.C. Many initiatives. They work with the Department of Energy, they work with Congress, various committees and bodies in both the Senate and the House. They work with the executive branch to promote the interests of the nuclear power industry. And they are now taking the Advanced Monitoring Project and developing and using it as use cases to promote regulatory transformation for the industry through the Nuclear Regulatory Commission. They're also helping scrub various federal departments to help us fund phase 2 of this project as well. So again, bringing along all of the stakeholders as around your technology, your innovation initiative. It's very important to bring them along to gain their acceptance and support. And another entity that had its birth from the Atoms for Peace initiative is the International Atomic Energy Agency. And so this is based in Vienna, and interested IAEA, our project has captured their attention. And we're actually working with IAEA now to develop international guidelines for the adoption of artificial intelligence in the nuclear power industry. And I must thank Dr. Shankar, who originally alerted us to IAEA, this meeting that was held in May in Vienna, which got our initiative plugged into the IAEA's initiative. So helping bring along large-scale stakeholder acceptance on an international level. And so, looking ahead, we're just getting started. This journey, how do we know when we've arrived? Well, it's a journey, and in order to evolve to a sustainable future for everyone, you need to be ready to grow and scale as technology evolves. And so this is the model. This is what NewSuite represents. It represents from the upper left-hand corner clockwise, human cognition combined with intelligent cyber systems to allow humans to make better decisions more quickly. Integration, let's go down to 6 o'clock. Integration of field sensing technologies, both point technologies, fixed points in the plants, pressure, temperature, humidity, so on and so forth. And also as well as motor sensing capabilities. This represents drones and robotics. So basically being able to move sensors on these mobile platforms to where issues are emerging in your power plant. And this same model is similar to what's being used. There's IEEE papers around tele-autonomous ecosystems like this. And this model is being used for fleets of autonomous driverless vehicles, ocean-going cargo carriers with minimal crew, this kind of technology. And so we're building out this capability for nuclear as part of this project. And ultimately, where can we take this in the nuclear industry? Well, currently, just from an engineering and technical support perspective, every nuclear power plant has dozens of engineers on site today that provide power plant support. While we all love, having lots of opportunities from an engineering perspective, we can't afford that model. And with the majority of folks retiring at retirement age, there is opportunity to automate and transform following the attrition curve, and then training the next generation of nuclear plant specialists and engineers to manage digital technologies and processes, but with a much smaller head count. And so what the future can look like, rather than dozens of engineers doing things very manually every single day, this could be what an engineering and technical support center could look like in the future at a nuclear power plant. Not more than one person, but a much smaller footprint, armed with automated and mobile technologies in the plant, doing the inspections, the mundane walk around inspections and tasks and responses to things, and then bringing in valuable human expertise by exception when we have a chance. And people always ask me, what's the person's job sitting in the chair? Well, that person has the second most important job. His job is to feed the dog. And the dog's job, if you haven't guessed, is to bite the person if he touches anything in the support center. And so, stakeholder benefits, we're down to just a couple slides. So this project offers the participating utilities an opportunity to automate complex and burdensome tasks to free up their staff to perform more valuable activities, strengthen safety, performance, and reliability of nuclear power plants by near real-time monitoring of important processes and activities, as opposed to hourly inspections or shiftly inspections, almost real time. So we will know immediately when something in the plant is changing. Nuclear industry, we're developing a strategic roadmap for transforming technological transformation. We intend to make this all available to any other nuclear utilities across the country, and support with a supporting business case. And for the United States of America, this will help enable us to sustain the benefits of nuclear power, to support energy security, independence, grid reliability, preserve our nation's single largest source, if not the world's, well, it is the world's single largest source of zero carbon generator capacity, and reduce the need for federal subsidies to maintain our inefficient processes. And so with that, in closing and in summary, technological disruption, environmental priorities, economic realities are bringing about a radical transformation of the energy industry. Working together, we will preserve atoms for peace. That's what we're committed to doing. If you'd like to learn more about the project, this last slide, there is a link to a feature editorial from, this is a couple years ago, but it's a good overview of this project that you'll find in Nuclear News. And if you have any questions, always feel free to reach out to me, and I will respond. And with that, Dr. Shankar, that concludes everything I have, and I'm glad to answer any questions.
Oh, terrific, Clint. Thank you again. You know, as I mentioned, I worked with Clint for many years, and never tire of his presentations because there's always something new. You know, the fact that it's been evolved, all these technologies have evolved into a business process that can be justifiable is just a great thing that's happening. Thanks a lot, Clint. And, you know, especially with nuclear power, I expect that to be a very strong player in the energy transition, at least, if not in the, as we go forward, as one of our strong options in generation. Thanks a lot, Clint. So, question and answer time. And as we've done before, I would like to have the students ask questions first. Students, please unmute yourself, introduce yourself, and ask Clint that question. And then we'll go around until we have addressed all the student questions, have questions from the general audience. So we can now, if you want, Clint, you could take the slides off the screen so you can see everybody.
I'll try.
Okay. Are you able to see? Are you able to see people?
Yeah. Yes, I am.
Okay. Good. All right. Listen, I apologize on behalf of Clint. Clint is a really good-looking guy. You know? He's not just a slide. Please, questions in the audience from students. Please unmute yourself and ask that question.
Hi. I have a question. First of all, thank you so much for your presentation. That was very interesting. And I definitely agree that nuclear power will be a very key piece in our energy transition. So my name's Ava Hudson. I'm in my last semester of the ESE program. I have a background in environmental engineering. This is slightly unrelated to your presentation, but my capstone project is looking at the feasibility of installing SMRs at decommissioned coal plants. So I was just curious as to what your opinion was on SMRs and if you think they'll become economically viable in the future, or if you think it's still large nuclear plants are the answer. So yeah, anything that you have relating to that would be awesome. Thank you.
Okay, well, thank you, Ava. Yes, small modular reactors offer a promise for the future. These first SMRs are going to be expensive, but that's the way every technology starts. You go rewind 10 years or so ago, solar couldn't compete, wind couldn't compete. Rewind, nuclear needed subsidies to get off the ground. Coal needed subsidies to get off the ground. There's a timeline and a process to take these new technologies and scale them. And a lot of times we need subsidies to help promote them getting to scale. So I think you probably know better than I do. I haven't looked in a year or so, but I'm thinking SMR technologies is probably the operating cost is probably around $100 a megawatt hour, for installed SMR right now, compared to, the average market clearing price of power these days is probably around $30 on average. So the thing is that they will become more profitable and they will scale, and there's so many, all of this, I'm sure, but there's intrinsically safe, much smaller footprint, highly reliable, can be operated remotely from a central location. So I do see them having playing a very important part. The challenge is, we're still years away from the first SMR becoming operational. And then as we scale up, there are decades to get SMRs, decades of construction ahead to get SMRs to the generation capacity of our current nuclear fleet. And so we need to maintain the legacy nuclear fleet for those reasons, to help bridge the gap and maintain high levels of reliability until other generating sources such as SMRs and more reliable renewables, which would be improved through battery storage technologies and so forth. So all that needs to come together. So I've kind of wandered around a bit there, but yes, I'm very thrilled with SMR technologies and microreactor technologies that are also on the forefront going forward.
Okay. Thank you.
One more comment on that. I'm sorry, Ava. You mentioned putting SMRs at where coal plants are being shut down. I think that's a great application. And the big benefit there is, all of the transmission and distribution, all that infrastructure is there. And so my company here in Texas, Vistra Luminant, we're actually, building battery storage capabilities at adjacent to the coal facilities that we are currently involved in shutting down. And we do have our eye as well, eventually maybe putting some SMR generation capability there. So yeah.
Great, thank you.
All right. Again, questions from students. Please unmute yourself, introduce yourself, and ask a question. Students.
Hey, there I am. I figured it out. Can y'all see me?
Yeah. All right. All right, Clint. Better late than never. I see John McCauley from Pico has his hand up. John, go ahead with your question.
Hi, thank you. Two questions. One is a sort of a lighter one. How does the robot dog get through the heavy airlock doors to get into primary containment to see if there's nothing on fire. But my second question is, so you have 90 some nuclear units now in the United States, and under optimal conditions, if everything goes right economically, technically, with license extensions, et cetera, I mean, eventually they have to retire, I would assume, at some point, right? And then the next generation nuclear takes time to come online. I mean, so if you were had a perfect crystal ball, would you see on a net basis a dip in the amount of megawatts that are in the United States as the old stuff retires before the next generation comes online? Or do you think it can keep itself reasonably constant in terms of megawatts? Not growing, because everybody in my RTO is PJM, and they have their own forecast about growth with EV and the electrification and everything. But the nuclear component of things, do you see staying constant, or are we going to see a dip? I mean, I think I'm a big fan of nuclear. I started in nuclear. I crawled around the Limerick nuclear plant in Peach Bottom earlier in my career, and I think it's essential for the future, but not everybody shares my views across the United States.
Well, John, I share your views, and so what we're doing I think it's possible that we can sustain our current legacy nuclear generation capacity going forward. In fact, as a part of power uprates, we've actually been able to install in gigawatts to derive additional gigawatts of power from the legacy fleet. And there are a number of the plants that are all working through power uprates now, or a second power uprate for their facility to get even more power out of them. So we've got that going on. We are at risk of a dip in generation availability, and I would broaden this beyond even nuclear. As you mentioned, electrification of transportation. If we do indeed electrify all of the transportation industry, just as one data point, we would have to double the generation capability currently available in the United States. So we would need to double the number of, well, I think I've just said it, but we need more nuclear, and we need it now as quickly as it can be built, because there will be a dip if we really do electrify transportation. Right now, we don't have the infrastructure. So we've got a challenge there, and so more generation, more energy storage is going to be critical to support that disruption, technological disruption of the transportation industry.
Thank you.
All right. Questions for Clint?
Oh, and I guess one other thought, back on John's question. Sorry, Ramesh. The existing nuclear plants were originally licensed for 40 years. Many of those plants have reached their 40 years or approaching their 40 years. Many of those plants have applied for a 20-year extension and received a 20-year license extension. And some are actually approaching their additional 20 years, and are going for 40 years. And so we are ultimately looking at the legacy fleet, assuming material conditions are sustainable, and we believe they are, and our data is saying they are. These plants the existing fleet is expected to have lifetimes now of 80 to 100 years. So yes, we can help bridge the gap to new energy platforms with legacy nuclear. So there's a lot of promise there to keep that going if we're focused. And you mentioned Limerick. You may be aware of it. Limerick's got a big research grant going on right now, and they're modernizing. They're going from analog safety and control systems to fully digital, and that's being funded as a research project to learn to help the rest of the industry transform. But Limerick's right in the middle of that right now to help sustain that plant for the long term.
Thank you, Clint. Questions for Clint Carter? Please unmute yourself and ask a question. Introduce yourself.
There's a couple in the chat box, Rudy.
Okay. Let me see that. All right, go by chronological order. Just read an article about current Miss America who's becoming a nuclear engineer. Comments?
That I can't think of her name. I've seen a lot of correspondence. Yes, the current Miss America. She actually was majoring in engineering and did her internship, I believe, at Constellation Energy. Please, someone correct me if I'm wrong there. But she did a summer internship, maybe, well, it was either last summer or the year before. And then went on to win Miss America pageant. And so, you know, she's now become quite the advocate for nuclear power, and the Miss America crowning of Miss America gave her a voice, a platform from which she could share. And so I'm very proud of her accomplishments and promoting a message that you know, to aspects of the population that you know, demographics that we don't typically access. So,
Okay, another question in the chat box from Alex. What are your projections for bringing the cost of nuclear operations down? How many plants will be able to stay in operation by reducing their operating costs? Will the industry need subsidies or carbon taxes to stay viable?
right now, we are getting subsidies through the Bipartisan Infrastructure Act and the Inflation Reduction Act. And those are very, very attractive subsidies, which is helping keeping some of the power plants running. The challenge is when those subsidies run out, unless those dollars are being invested to transform and to improve economics, they're going to be in the same, we're just kicking the can down the road. Mm-hmm. Nuclear power, when this industry was founded, offered the promise of too cheap to meter. And we weren't too far away from that. And we've added so much regulatory overhead over the years that costs have gone up. An interesting aspect of nuclear as compared to, let's say, coal or natural gas. In fossil plants, the single largest expense is the fuel they burn. In nuclear, it's the people. Over about half of the cost is associated with the people that have to do all of the stuff that's required to run the plant, to satisfy all the regulatory overhead, and so on and so forth. A nuclear power plant that was running in the mid-1970s had about 300 people on site. That same plant that's running today, the exact same plant, has over 600 people, and they've gone through a staffing reduction. So the idea here is we can operate without subsidies. We've got them now. We need them right now. I'm actually lobbying with our government to open up those funds and make them available to entities that are driving innovation initiatives and to entities that are looking to transform the economic model for this industry to help sustain them. So if we can target, transformation as opposed to just propping up an inefficient economic processes, I think we'll be better off.
Good, thank you. All right, and the next question, the chat box. Well, there isn't it. Here's the next question. I want to just expand on that, Clint. You're talking about this burdensome burden of excessive regulations. And I wonder if there's a role for AI, Chat GPT, to not only come up with smart regulations, what would be appropriate, but also help the technologists implementing it to look at what regulations would they be falling short of, so that there isn't that surprise factor that there's something that's done, in great harmony.
I was at NRC headquarters last week on attending a meeting on artificial intelligence. It's a long road to develop regulatory guidance for implementing AI. Part of the in nuclear, part of the challenge is, we think about, oh well, with all the unpredictability of artificial intelligence, what's that going to do to the reactor if we point it at the reactor? Well, from AI has come to include a whole spectrum of technologies, from advanced pattern recognition to the Chat GPTs of the world to autonomous control. And at NRC last week, we encouraged our regulators to think discreetly. Let's start on the non-safety side. Let's look at integration of AI someplace away from the reactor, but balance a plant to help capture learnings and migrate slowly as the technology matures. I think what technology, AI ultimately is another tool in the toolbox, and where it makes sense, let's use it. But all technologies, can bring value. And so we need to focus on what problem we're trying to solve first, what technology is available to solve that problem. And I think there's the opportunity. Anything that we can do to automate data collection, automate analytics, automate reporting and compliance, and all the costs for doing all those things manually. Automation to drive cost out of the business is where I see technology being the most valuable. And it will, and as far as AI, I actually asked the question of one of our regulators. He was talking about, how rapidly AI is moving, and we're going to struggle to keep up. And the way we do things, it's going to take us 10 years to develop guidelines and regulations for the industry. And so when asked, well, why don't we just point AI at all the regulatory stuff and let it generate something for us to start with? After a moment of silence, the NRC's representative responded, well, this was a public meeting, so I'm not giving away any secrets here, but he's saying that would just be garbage. Chat GPT cannot develop regulatory guidance. And so we got a ways to go.
A question in the chat box here, Clint. What are your thoughts on the issue of nuclear waste?
All right. I'm glad somebody brought that question up. It's one of my favorite topics. I am not concerned with nuclear waste at all. All of the high level, I'll start with how big of the problem is, and then what opportunities are there to deal with it. So first, how big is the problem? We've been running this industry since the 1960s. And if we take all of the high level radioactive nuclear waste and put it on, let's put it, on the Philadelphia Eagles football field, piled it all up, okay, decades and decades of high level radioactive waste, it would cover the football field 100 yards by about 30 feet high. That's all. We've powered 20% of we supplied 20% of our nation's industry. That's the size of the footprint from a high-level rad waste perspective. That being said, all of that high-level waste, it's basically the spent nuclear fuel. That fuel can be reprocessed. And actually, almost 95% of that spent fuel can be reprocessed into new fuel and used again. And there's actually companies that are moving in that direction right now to reprocess nuclear and basically reuse that fuel. And so you would be driving, if we can do that, and actually our former DOE's Office of Nuclear Energy, Secretary of Office of Nuclear Energy, Ed McGuinness, I believe. He's the one that's leading, I can't think of the name of his company, but you look at Ed McGuinness, Office of Nuclear Energy, his website should pop up. But he's actually building a company and has plans to have a production scale factory up and running to reprocess fuel by the end of the decade.
I think Bill Gates' company does something similar, the tearaway reactor.
Yeah, TerraPower. I can't.
TerraPower.
Yeah, I can't think of what they call their nuclear fuel now. I'm sorry, Ramesh. I don't recall what I don't recall their terminologies, but I'm not certain where they have a new type of fuel. It's just escaping me right now, the name, but it is, they may be the ones using the pellets. I'm sorry, I just can't think of the name. It's a much
I don't think pellets, yeah.
It's a much more stable fuel,
Yeah.
a much more effective geometry, a lot safer, intrinsically safe nuclear fuel. I don't think it's spent nuclear fuel. I don't think he's doing that yet, but we could. TerraPower, NuScale, all of those could ultimately adopt reprocessed fuel if we went in that direction.
Yeah. All right. Questions for Clint from the audience? Please unmute yourself. We've been on the air for more than an hour. You should be more relaxed right now. Students? Questions for Clint? So we do have an answer for who Miss America is, and Melissa. Melissa, do you want to announce who she is and her qualifications, or go ahead?
Oh, sure. So Grace Stink, I think that's how you pronounce her name. She was Miss America in 2023. And she's been a really strong advocate for nuclear energy and nuclear power. She's actually a senior nuclear engineer, I think, at the University of Michigan. And she attended the Women in Nuclear conference this past July and had a really good speech at that conference. So it's great to have that public advocacy for nuclear power.
Absolutely.
Thank you, Melissa. Questions for Clint?
Rudy, Alex had another one. Alex, one of our students. He said,
Okay.
so how many people do you believe a plant should be able to operate on? Can we bring that to 600, that 600 person plant back down to 300? Can it be lower?
I'll quote one of our industry executives, Chief Operating Officer of Xcel Energies in Minneapolis, Tim O'Connor. His vision is 100-person station. I don't think we even Tim doesn't believe we'll ever get to 100. But if you look at what does it take to operate the physical complex, about 100 people can do it. That doesn't count security. You got to have nuclear security is the single largest department at any nuclear plant these days. But except for the security thing, you can operate a nuke plant with 100 people. And so to answer the question, can we get back to 300? I completely believe that we can. And the reason being is, again, the regulatory overhead is not just formal NRC regulation, but it's informal regulation through, for example, the Institute of Nuclear Power Operations, INPO. INPO is it is us. It is the nuclear utilities. We've stood up IMPO to help serve the entire industry, and we've created a lot of guidelines and standards and that we've required the nuclear plants to also operate under. And so these aren't required by regulation, but we've chosen to do certain things. Another item, here's another opportunity as an example. Again, all the formal regulation we put on top of ourselves. Right now, one example that hits me personally is came out of the 3 Mile Island accident. After TMI in the late 1970s, we are required to have an engineer on shift 24/7 at every nuclear plant control room to provide reactor and thermal hydraulic engineering advice during nuclear accident conditions. Shift engineers, shift technical advisors. I was one for many years. That's required by regulation. Since then, we've improved the training and the quality of training for all nuclear power plant operators. And we've incented our control room operators of shift supervision to get college degrees, technical science degrees. And now with the advent of machine learning intelligence and everything the technology brings, do we really need an on-duty shift engineer 24/7 by 365? So again, we can unbundle maybe outdated and unneeded regulations. So again, targeting all that and driving it out and using technology to satisfy, the appropriate regulatory requirements for the industry. Yes, we can get back to 300.
Okay, good. What about SMRs? They probably are geared for a smaller work base, the standardized design, and so there a lot of it is directionally, I think, probably a good thing that's happening.
I would say dozens will probably be more realistic for SMRs, in terms of rather than hundreds. And, the being intrinsically safe, when the plant, trips offline, operators don't have to touch anything. It takes care. It takes care of itself. So, yeah.
Yeah. And I was just reading this news item, Clint. The next Mars mission, which will go, I guess, another couple of years, is going to take a rover with it, but apparently that's going to be nuclear-powered rover, so that it has longer duration.
Yeah, we've used nuclear power for the Voyager and Viking spacecraft. Basically, what these things are, think of them more as a battery. They're not nuclear fission reactors. It's just radioactive material that's decaying and generating heat. When I think in some of the space missions, I think they've used some plutonium, but it generates heat, and that BTUs, that heat emission, can be used to generate electricity. And then, in terms of small, I would say several kilowatts, but that can run for years and years and years. Not certain what the rover on Mars will look like. It may be another nuclear battery using radioactive decay for thermal, to access heat to make electricity. I have seen development work at the national labs, and we are targeting space reactors, nuclear reactors, to be used in future spacecraft. And you can go Google. I think Idaho National Labs is definitely involved in that initiative.
Yeah. All right, question for Clint. We still got about a few minutes.
There's one more still in the chat, Rudy. Sue Glatz asked, what are your thoughts on the issue of nuclear waste?
Yeah, I think I just voiced that.
Oh, okay, sorry.
Yeah, I can answer it again, but it'd be the same answer.
Wasn't sure if he changed in the last 5 minutes or so. Just checking.
One other thing. Go ahead. If you got.
No, I was just going to ask Sue Glatz, are you satisfied with the answer?
Yes, thank you. I appreciate the answer. It was very helpful.
All right, thank you. All right, go ahead, Clint.
I was just going to make an off-the-cuff comment what to do with the spent nuclear waste. I'd love to have one spent nuclear fuel assembly, and I'd put it out there to heat my pool in the backyard. So
Oh,
another way to get rid of to clear them off that football field in Philadelphia.
a spent nuclear rod in every house or something. That would be the new jingle.
It worked.
Ah,
No,
right.
that wouldn't be from a nuclear safety, nuclear security concern. That's probably not a good idea, but it would work.
Yeah. All right. So there are no other questions. Thank you very much.
Hey, Quint, this is Frank Richards. Can you guys hear me? I'm sorry.
Yeah,
Hey,
Frank.
go ahead, Frank.
Okay. Just we have Barnegat Bay, Oyster Creek was a nuclear plant that shut down in 2019. And apparently the big reason for that is that was warming up the bay because they didn't have any cooling towers. And the which is not a good thing, but the folks who own the plant said, no, we don't want to do it. So they shut it down. Is there any potential to like bring something like that back?
Well, there's a long answer. The short answer is yes, we could. And that's a perfect example of not being able to economically compete. Those cooling towers cost a whole lot of money. Another option would have been for them to just run at reduced power level so they stayed within their environmental discharge limits for discharge water temperature. But again, economics, they couldn't run at a reduced power level and pay the bills. So I'm not sure where in the decommissioning process Oyster Creek is, so it may be too late, but Palisades in Michigan, I think, that plant shut down earlier this year, and Holtec is a decommissioning company. They go in, they tear down nuclear power plants, sell everything for scrap, take care of all the radioactive stuff and restore. But in the case of Palisades, they're saying we want to restart it. And so the answer was no way, no how, but the plant is still there. And now I saw last week, I think they've signed a contract with some of the local cooperatives in Michigan who want to buy the power after Palisades restarts. And they're lobbying with the government to tap into federal funding to bring that plant back. So I'm optimistic. Palisades is one of our oldest plants, but if that plant, if the structural integrity of the components and the systems is still there, there's no reason we can't procure new nuclear fuel and start that thing up again. I would say it will in reality probably take 2 to 3 years from right now to reacquire and retrain the workforce to operate the plant, but it's happening. Seems like it's happening.
All right. Thank you, Clint. Anyway, there are no more questions. I think we'll call it a day. When you brought up the Oyster Creek, I was reminded of one of my very first jobs that I did was to collect digital data with a Biomation 6100 at the Oyster Creek plant, looking at ultrasonic signals so we could process it digitally outside. So we've come a long way. And I just want to announce that next week we have a presentation by Vikram Budhraj. He's the CEO of Electric Power Group. He'll be talking about the integration of large-scale renewables and the issues and challenges. So that should be a very interesting talk. Thank you again, Clint, for a very informative presentation. Thank you, audience, and I look forward to seeing you next week at our seminar number 4 at Lehigh University. Thank you very much.
Thank you all.
Thanks, everyone.